Hello, everyone. Megan, Tessa, and I decided to do our presentation on helicopters, the history of the unmanned helicopter. The earliest recorded reference of vertical flight comes from China in 400 BC, which came from a children's toy which worked by using a rolling stick attached to a rotor. Releasing it would cause the toy to shoot upwards. In the 1480s, Leonardo da Vinci created a design called the aerial screw. In 1754, Lomonosov developed a similar model to the Chinese toy, which relied on a wound-up spring to produce the power. In 1861, inventor Gustave de Ponton de Amécourt attempted to use a steam-powered model, but it failed to ever lift off the ground. But his attempt was important for two major reasons. He first coined the term helicopter, and he was also the first one to use aluminum for his aircraft design. In 1878, Inercio Florinini built an unmanned steam-powered machine that was able to get 40 feet off the ground and hovered for around 20 seconds. In 1885, Thomas Edison created a model by using an internal combustion engine. It eventually failed due to an explosion. From 1901 to 1905, John Boyle was able to make the internal combustion engine work. In 1901, he first achieved a hovering height of just about 2 feet. But 4 years later, in 1905, he was able to reach a hovering height of 13 feet and was able to travel 4,900 feet horizontally. So, the history of the manned helicopter. In late 1907, French brothers Jacques and Louis Bergout were able to get their gyroplane number 1 design to reach 2 feet in the air, and it hovered for about a minute with a pilot inside. The things were, though, it required assistance to remain steady. But later that year, a Frenchman named Paul Cornu was able to lift himself for only about 20 seconds off the ground, but he did not need any external help. In the 1920s, Raúl Peturas from Argentina invented the cyclic pitch, which was the ability to tilt the rotor without needing an extra propeller, and auto rotation. This is essential for helping land damaged helicopters. And here are what early helicopter designs look like. Here you can see the Chinese flying top, Leonardo's vertical screw, and many others.
9 years before Igor Sikorsky created the helicopter, he expressed a vision he had for an aircraft that had more control and the ability to take off in a small area. And these two aspects of flight are very important in highlighting because they had yet to be done. We'd seen successful horizontal flight with airplanes, and as you know, airplanes require runways, which take up a lot of space. It takes a lot of area for an airplane to actually travel before it's generated enough thrust and lift to get up off the ground. So essentially the idea behind a helicopter and vertical flight is convenience. You can land and take off in many more areas than you would be able to because you don't require the space needed for an airplane. In 1989, we see the two horizontal and vertical flights come together to create the Bell Boeing V-22, but we'll talk about that in a bit. And Sikorsky really had to focus in on what he knew about vertical flight. He knew the 4 forces of flight: drag, lift, weight, and thrust, all pulling in different directions, but he really needed to hone in and modify it to know how this can be changed for vertical flight. Essentially, he came up with the helicopter, and instead of what used to be wheels on the airplane, you see a landing skid. Also, there's a cockpit, passenger seat, and engine, all formally laid out with previous aircrafts. But in a helicopter, you introduce a tail rotor, a main rotor, and blades. Now, these blades derive rotation from the engine. Specifically, it's a turbo engine, and These engines work very differently than those on airplanes. Airplanes use their engines to actually generate the thrust force itself. However, the primary function of a helicopter's engine is to harness the air, compress it, and go through turbines and actually just turn the rotor shaft. So, very different uses. But these rotor blades are very, very important. They were designed with much intention behind it. The airfoil technology is used, and it's designed in a sense that will conform to Bernoulli's principle with a curved top and flatter bottom to generate more lift, helping the helicopter to get in the air, and it's essentially what keeps it airborne. But Newton's law, Newton's third law states that for every action, there is an equal opposite reaction. So that means that as the rotor blades would be spinning to create that thrust, the actual helicopter itself would slowly be moving in the opposite direction, creating torque, which would not allow for the helicopter itself to be controllable. So that's the purpose of a tail rotor. So it ensures that the aircraft remains stable during the flight by counteracting the torque. So it's actually moving in the opposite direction. And helicopters that don't have a rotor tail will have a um, secondary rotor that's attached just beneath the main rotor, and it's mounted right there to counteract the torque that would be created by the main rotor. Because we're no longer flying horizontally, the four forces of flight are now in a line, which allows for the helicopter to fly vertically and also hover. As mentioned before, the thrust is actually produced by the rotation of the helicopter's blades itself. And these blades in the main rotor are actually on what is called a swash plate, which allows for movement within the rotor itself, allowing for directional changes. So a helicopter can also go forward, rearward, sidewards, and vertically remain. One thing that's very important to point out is that helicopters can still move. And so as they do that, when it moves, the helicopter moves at an angle and the force produced by the blade is not vertical. So the horizontal component of this force will make the helicopter move in the desired direction, but the vertical component of the blade will force the balance of the gravitational or weight force. Another thing that is very important in introducing is the terminology of directional flight for a helicopter. So lift is produced by an airfoil that varies with the angle of attack, and this lift is now referred to as collective lift. Also, the movement of the swash plates in the main rotor keep the blades in respective balance, resulting in directional changes. So this is now called cyclic pitch.
For rigid-winged aircrafts such as airplanes, airflow is constant over the wings, so Bernoulli's equation can be used to determine the force of lift that is needed for specific planes. To calculate the force of lift on a helicopter or rotor aircraft, an integral version of Bernoulli's equation must be used because the airflow is different at different points along the blades of the rotor. In this case, velocity is a function of the rotor's radius. The velocity of the air over the blades changes as the radius of the blades change. Air travels faster over the blades towards the center of the rotor and moves slower towards the ends of the rotor blades. Tilt-rotor aircraft are machines that combine the capabilities of both airplanes and helicopters. This allows for them to travel with the speed and range of a plane, but also have the maneuverability of a helicopter across multiple planes of motion. Tilt-rotor aircrafts, such as the V-22 Osprey, are designed in such a way that allows them to take advantage of the best parts of both planes and helicopters. The rigid wings and thrust produced by the engines of planes increase the speed of travel and the range that can be traveled, while the rotors of helicopters aid in maneuverability in the longitudinal, lateral, and vertical planes of motion. This results in the Osprey having a max speed of 306 miles per hour and a travel range of 990 miles. These aircrafts are also capable of vertical takeoff and landing, which means that they do not have to rely on the use of a landing strip. This mechanism of takeoff is also what makes it possible for the Osprey to hover in one spot by creating lift without forward propulsion. Once it is in the air, the Osprey is able to transition between 3 different modes during flight based on the position of the rotors and the nacelles. The nacelles are the casings at the end of each of the aircraft's wings that house the 2 individual 6,150 horsepower engines. In airplane mode, the nacelles are kept at a 0-degree angle. Lift is created by the forward propulsion of the plane, causing high-pressure air to move under and low-pressure air to move over the 84-foot rigid wings. In VTOL or helicopter mode, where the nacelles are at a 90-degree angle, the aircraft relies on 34-foot rotor blades to create lift. The rotation of the blades creates the same high-pressure and low-pressure environments above and below the blades that causes the lift on the wings of planes. Finally, in conversion mode, the nacelles can be positioned anywhere between a 0 and 90-degree angle. The production of lift in this mode is split between the rotor blades and the rigid wings of the aircraft. The Osprey is able to transition between the VTOL and airplane modes in as little as 15 seconds in the air. The V-22 Osprey has had a recent history of fatal crashes during training accidents and missions, but these accidents have led to increased safety measures aboard the aircraft. Almost all the systems aboard the Osprey are redundant systems, meaning that if one system stops working, there's a backup that can take over and ensure either a safe landing or continued flight. The Osprey also relies on fly-by-wire systems. When the pilot moves the controls, the movement is converted to digital signals that go to a computer, which makes the necessary changes. In another effort to increase safety, the engines located in the nacelles on the ends of each wing are connected by a drive shaft. The drive shaft connects both engines to both rotors, making it so that if one engine fails, the rotor will still receive power from the other engine, preventing a crash and allowing for the flight to be carried out. The increased capabilities of the Osprey increases its usefulness in a variety of different situations. Its ability to hover like a helicopter make it perfect for search and rescue missions both at sea and on land. Its speed also makes it a good option for medium-range assault missions performed by the armed forces. In missions such as these, speed can be extremely important, as well as being able to land and take off quickly. Finally, the Osprey is useful in situations such as long-range missions or personnel transportation because of its greater range of travel and increased landing and in-flight maneuverability. This video shows the active transition from VTOL mode to airplane mode during the flight of a V-22 Osprey. Thank you for watching our presentation.